or the secondary?
Neither. The problem is that in the Lagrangian, if you start gauge fixing, you lose equations of motion. For example, if you substitute A0 equal to 0, so there is no A0 in the Lagrangian, you lose the Gauss law. Okay. So it is necessary to have that A0 in the Lagrangian to get the Gauss law. But when you go to the Hamiltonian formulation, it starts telling conditions on the initial data, okay, or even the Lagrangian formulation. So if you just look at equations of motion, you can recover the constraints directly, constraints on the initial data directly. Okay. So the redundant variables are not so redundant in the variational method. Okay. So you cannot say primary or first gauge, you cannot say like that.
Another in literature there is another sometimes statement that you give me any theory, I can make it a gauge theory by adding auxiliary field. So the gauge property is not very fundamental.
That is problematic. Dirac in his book, he gave a set of lectures in Yeshiva, I think, okay, where he analyzed this constraint dynamics first, okay, and there he says that, for example, diffusion constraints, any theory can be unparameterized. Well, he doesn't use that. You can always introduce at the level of the action new variables and make it completely gauge diffeomorphism invariant. Okay, okay. So that is the kind of thing you are talking about.
But
okay.
Then it loses the very fundamental meaning.
Or
there is something which I am missing.
I mean, if you do the gauge analysis on those systems, then generally speaking they get eliminated. There is nothing much more happens. But in other cases where you get twisted bundles and so on, like the ones I am considering, you cannot do that. Okay. Or in gravity there are conditions at infinity, then you cannot do this. Okay. I mean, so I think there are trivial cases and non-trivial cases, I would say. Which one?
Massive Maxwell field.
Proca, no, because that gives you a condition on when you vary A0, okay, which tells.
No, it's not a gauge theory, but I can add auxiliary field to make it a gauge theory.
dmu of that is this equation. This is oh yeah. Stuckelberg formulation. Yeah, right. Yeah. Okay. Massive electrodynamics is not a gauge theory. There is no gauge transformation. There are constraints. Okay, they are all second class.
So that's what. So the existence of constraint and existence of gauge transformation as gauge
should be separated.
I have one question. So how do you, given a Lagrangian, how you can just know that there is a constant in the theory? If the primary constant is zero, if the first moment is zero, then you can say there is a constant, or there is another way to characterize there is some constant in the theory given a Lagrangian.
Given Lagrangian, I mean there are two. Let me say, if you make a Legendre transform, you will know immediately, because you will find that the.
For Legendre transformation, you have to calculate the moment of the theory.
Right.
And that turns out to be zero, then you say that there is.
So it is a statement that the dpi or dqj dot, okay, this object here is this is a Legendre transform, right?
Yes. Of the P.
This is the one which tells you whether I can invert. If I make a Legendre transform, I can go back. Okay, but this is equal to d2l dqi dot dqj dot, right?
dqi dot dqj dot.
Right? But this is a Hessian matrix. So the singularity, the existence of kernels in this mapping is the same as this matrix having not zero determinant. Okay, so you can directly look at the Hessian in the Lagrangian formulation. This is called the Hessian matrix, and you can tell whether there are going to be constraints. There are constraints in the model.
So primary constant has to be zero for any theory.
Any theory, why?
Otherwise, how this I think is zero.
If the theory has a Hessian which is singular, there will be primary constraints, and vice versa. But if you take a free particle, there is no nothing, no.
You should think of it as a submanifold. That's all.
Yeah. You cannot invert it. The tangent space is not from one to the other is not matching properly. Okay. So last time what I did was, this time I will start by searching for a duster.
Yes, there.
Yes. So let me just quickly remind you what I did. So we had a manifold M, right? This is the what is governed in the Lagrangian. Associated to it, you have this space of positions and velocities, the tangent bundle and the cotangent bundle, positions and momenta, and the Legendre map. Okay. So any L will produce this map, okay, and primary constraints means the image of this map Pj gives you some constraints M P is weakly 0. Okay, the image of the map is 0. Okay, so the next step was from here you write the Hamiltonian, where you write the standard equation Pj, say Mj dot. You should really write Mj dot minus L of P and M, not P and M dot, but you add Lagrange multipliers. Okay, and this we saw was a function of, this thing here is a function only of M and P. Okay, this is not unique. You can add and subtract constraints. All these equations are on this surface eventually. Okay? But you should not put this here, because when taking Poisson brackets, you will get wrong answers if you do that. Okay? After you do all your activity, you can set it equal to 0. Okay? Then you look at secondary constraints, say Pj, H, and you substitute equal to 0. Okay. I forgot to say that here may fix some Vj or give more constraints. Because in our spin problem, in fact, it fixes the V. Okay, it can do both. Keep going. Okay, so this will be more constraints called Sj. Okay, then keep going. Repeat till we stop. Still, no more new constraints. Then you have a whole collection of constraints. Okay, so we get a collection of constraints Ck prime. According to Dirac, primary versus secondary is less important. Okay, but what is important is to divide this into first class Fj and rest. Okay, call it rest as something Sk, Sl. where the first class constraints commute with all constraints. Okay. This has two consequences. Okay, the remain so. Okay. First statement is the matrix function, call it mjk of qp, which is the Poisson bracket of sj with sk of qp, is non-singular, okay, and invertible. This is important. Okay, why? If not, okay, there exists psi k qp, okay, not all 0, such that mjk psi k is 0. It is a null vector. Sorry?
Definition for first class constraint.
It is given right there. First class constraint commute with all constraints.
Yeah, but strongly zero, right?
No, weakly.
Again,
Everything is weak on the constraint surface. You take the Poisson bracket, evaluate it on the constraint surface, you get 0. So it is, as a Poisson bracket, it is acting tangentially to the constraint surface. Okay, the canonical transformations it generates, okay, takes a function on the constraint surface to a function on the constraint surface.
but all the constraints are already with respect to that. So you're not worried about primary and secondary constraints. Right?
No, not anymore. Okay, after you have done it, you collect them and divide them in this way.
So suppose the right hand side is a linear combination of ck.
Which one?
This bracket fjck Poisson bracket.
Uh,
If the right hand side is a linear combination of ck,
yeah.
would that be a first class constraint?
Yes. In fact, I will show you that the first class constraints,
But the Poisson bracket algebra, the Poisson bracket algebra of constraints closes.
Poisson bracket algebra constraints of the f's will close. In a strong sense, the Poisson bracket f with f will be an f.
So that's what you mean by first class constraints.
That is what I will deduce. Okay. Okay. So that is why I am doing this. This implies that Sj commutes with psi j, psi k, sk. Because the Poisson bracket is a derivation, that is, this is the same as Poisson bracket with this plus this with that, but this with this is multiplied by something which vanishes, right? Okay, but Sj with, let's say, Fl is anyway 0, because this is first class.
These SKs are second class constants.
I am not following you.
Sorry, these SKs are all the second class constants.
I want to show you that the Poisson bracket of second class constraints is invertible. Okay. It is fiber wise invertible.
Find this matrix.
Sorry?
No, I'm trying to.
But this is 0 anyway. So this will imply Sj, okay, is 0, not being first class. I said because the S will commute with all constraints n. Here, not this one. This combination, not this one. This combination. What is it? So what is it? There is a this one. Okay. Okay. So this implies but so I should write psi k sk fl for some bracket is weakly 0. This implies this, but this implies it already commutes with all second constraints. Okay. So I should have said or psi k sk first class, okay, which is contradiction. That's what I should say. Yeah, namely the existence, if this were 0, there will be some combination of the S's which is again first class. So I should have put it in the original list, right?
So you start with some SKs which are not first class.
So you have to collect them. So then it will imply that this is not 0. This
Understand this logic. So you start the rest SK. So these SKs you assume first they are not first class.
they are not first class. No linear combination of them is first class.
If the metric is positive, not some positive semi-definite, then there is a null vector exist.
Yeah.
And if I do that, so the null vector, and that this but statement is by definition, because that's the definition of first class constant.
Yeah.
Oh,
Okay.
Then it has to be first class.
Okay. Okay. So okay, I'll do this first. So we have therefore concluded that this MJK is invertible. Okay. Now I'll tell you geometrical meaning of what this is. Okay. So anyway, let me give an example. Okay. Then we can strongly eliminate second class constraints using what is called Dirac-Bergman brackets. I was not intending to do this, but since I will not use this in further analysis. What you do is, okay, this is changing the Poisson bracket. Okay, so you change the Poisson bracket, okay, in the following way. Change PB to, okay, Dirac dB. So it is, say, F1 F2 star is the original F1 F2, okay, minus F1 the constraint Sk, M inverse KL SL F2. Okay. Why am I doing this? For this bracket, okay, if you look at the bracket of Fj with anything at all, it is simply 0, because, for example, you put F1 as a constraint, it's a constraint, no? So you will find that this will become the matrix of the inverse, so it will cancel. Okay? So it is simply commuting with everything. So the Dirac-Bergman, in this new bracket, the constraints are in the center of the Dirac bracket algebra, Dirac-Bergman bracket algebra. Okay. Or
So what does this star mean?
the new bracket,
It's a Dirac-Bergman bracket.
huh?
It's a Dirac-Bergman bracket.
Bergman bracket, you have to check that it fulfills Jacobi antisymmetry obvious, but you can check it, but I will show you what it means. Okay.
So it's the center because it commutes with everything.
Everything and Sj equal to 0 you can eliminate it as an algebraic equation, okay, or Sj, okay, are in the center of, let us say, Dirac-Bergman algebra. It commutes with everything. So eliminated algebraic. So just eliminate it. Algebraically. I should show you some examples. What you do is some polynomial or something, you just solve it and get rid of the extra variables. Okay. This is not the best way in most cases, but I am telling for completeness that this is a methodology which has been pursued and works in some cases like massive vector meson. Okay. What does it mean? Okay. So first notice, note.
So you're using capital F for the first class constraints.
Yeah, I will come to that.
No, but these F's are any functions.
Any arbitrary functions, any function on the phase space commutes with this in this new bracket. What does it mean? Okay. So those of you meaning.
S1 is to commute.
Huh?
S1 is to will commute.
Sn S2 of course will commute, but this Ss will commute with anything in this star bracket, okay. Everything whatsoever, and we want to work on the surface Sj equal to 0. These are all classical. Quantum, you could have all kinds of problems with factor ordering. I won't touch them now. Okay. Okay. What is the meaning? Well, remember. Okay. So, in all these problems, okay. In all these problems, we have a what we will call a symplectic form omega, which I will write this in the notation omega ij d psi I with d psi j. Okay. This is your dpdq. In local coordinates, you can always bring it to this form, but you have some.
Why is it two form?
Huh?
It's a two form option.
It's a two form and is closed. Okay, and Poisson bracket, okay, is given by any two functions, say alpha beta, is given by this omega. I am not sure of the indices. Let's see. I have to be sure of. Yeah, it's okay. Index notation. Okay. Okay. D alpha over d psi I, d beta over d psi j. Oh, I have to invert this. That's right. That's fine. Where omega I k, omega k I, k j is delta I j. Okay. This is a symplectic form. This is called the Lagrange. This is Lagrange form. Lagrange bracket. You might have seen come across Lagrange brackets. Okay. This is associated with the Lagrange bracket. So. and this, you can think of it as dp dq, fine. So here the omega ij will be the epsilon tensor, antisymmetric epsilon tensor, and you put it here, you get the Poisson bracket. And the fact that the closure, okay, d omega equal to 0 implies and is implied by Jacobi for Poisson bracket. There is a little known paper by Pauli who showed this first. It was Pauli who showed this first, okay, that this closure of the, he was the first one to start discussing this Poisson algebra, whereas the symplectic manifolds were already known. There were theorems on closed two forms and so on. Pauli addressed this in classical mechanics. Now what is happening with this surface? Okay. Now, okay, the surface, okay, the number of independent Sk is even. Why? Because, okay, we know that MKL is equal to minus MLK, right? It's antisymmetric. So determinant of M is equal to minus 1 to the power of D determinant of M, okay, D number of SS. So if D is odd, the determinant will vanish and M will be singular. So number of SS is even, okay. So if original phase space, original, say this object had dimensions, let's say is twice, let me use this notation, M is a dimension of the manifold, okay. The dimension of surface, okay, with Sj equal to 0, okay, is 2m minus an even number, okay, because the number of constraints, independent constraints, is even. So this is an even dimensional submanifold, okay, in T star m. So the surface, okay, in T star m, okay, with Sj being 0 is even dimensional. Okay. So you have this T star m and you have this surface Sj equal to 0.
This is nothing to do with constant method.
This is a constraint surface of second class.
Of the second class.
Of the second class. So you have a form here. In the whole T star m you have this symplectic form. Forms can be pulled back if you know what I mean. Okay. So you can restrict the forms. Okay. So this is my constraint second class surface. I need some, it's even dimensional. So I pull it back. Usually this surface, give me some surface S. S is not a good word. Huh? What? Sigma. This is even dimensional. Okay. So you can pull back. So omega, I can pull it back. Pull back of omega to sigma call it phi star or sigma using the canonical notation. So actually what people will say is, think of the sigma sitting outside here, and you make a map of phi or sigma embedding it in this T star m and pull it back and put it there.
So basically, the Dirac bracket makes it Lagrangian submanifold.
Sorry?
Dirac bracket makes this submanifold a Lagrangian submanifold.
It is not Lagrangian,
Not Lagrangian.
okay, but it is a symplectic manifold. Because this
Omega
two
will vanish on the.
omega will not vanish. That is the whole point. On a second class surface, this pullback form is a closed two form. It's closed because the original one was closed, but it is non-singular. Okay. Then write phi star omega, okay, as phi star omega ij d psi I wedge d psi j. Okay. And Dirac dB bracket is just obtained from here. That is alpha beta star is alpha beta minus, okay, alpha, okay, well, I shouldn't write like this, is obtained by inverting this matrix phi star omega ij d alpha or d psi I d beta or d psi j. Okay, the pullback form. Okay, and since d of phi star omega is 0, because a pullback doesn't change the closure, Jacobi okay is guaranteed.
The submanifold is also a symplectic.
Symplectic manifold for second class constraints, only second class. Okay, this result I should absolutely mention was proved by Mukunda and George, and there was some other people who proved it at the same time, but definitely these two proved. George Sudarshan, and yeah, these two. Main problem is in showing that this expression coincides with what Dirac and Bergman wrote down. Dirac's answer is given in the Yeshima lectures. Bergman independently was working on this. There is a story which Haag told one of my friends. Okay? Haag was asked, somebody discovered that Haag had originally written a paper on constraints. So he was asked why he left it. He said that he was very young and he heard that Bergman was working on it and Dirac was working on it. So he said he was simply not good enough to quit. So there is a small story. Okay? But if you don't know differential form, never mind. Okay? Yeah.
How is this reduced to the case when there are
No second class constraints.
Yeah.
Then you don't do it.
No, but you're pulling back on a surface.
That surface will be the whole manifold. You don't do anything. Okay?
No second class constraint would be no that.
No. T star m is there already. T star m is there already.
Yeah.
And second class constraints gives you a submanifold there.
Yeah, so if there are no second class constraints, there will not be a supply.
But you will be just working on full T star m.
There are no second class constraints, the whole time. 4T star m.
Yeah.
Manifold itself is a subset.
Whole of T star m you will be working.
But the complement of that is the whole.
No, not the complement. This is a submanifold. By the way, you cannot find a complement of a submanifold. That's not a manifold. Huh?
Yeah. You can make that.
Think about it.
Okay. So this is just a geometrical meaning of this mysterious formula.
It's not clear why this is Dirac bracket. This is clear.
It is not. That is not clear. That was the contribution. I mean, the guess that this is what was happening was done by George and by Mukunda, and by somebody else, whom I am not remembering. Okay, and they wrote a. Mukunda is very clear and explicit. So that paper is very precise and shows this fact. You have to go and look at the constraints, okay, and invert the matrix and use properties of the matrix systematically, okay, which they did.
So SS commute would be a hint that you have the right answer. Because starting the original point of bracket, SS don't commute, you get something.
SS will not commute.
So
The SS.
so you should be able to show that this is commute.
Yeah, yeah. Because SS are gone. Because you have put when you pull back here, there are no SS. Okay, it's already a simplicity. It doesn't know anything about SS. See, when you look at this language, the sigma is not supposed to be inside. When you do the pullback, it is somewhere there. You have a model manifold sigma. You pull it, put it there, and pull back the whole structure. So then it doesn't know anything about where it came from. Okay. So that is why I put a 5 star that language. Okay. But if you want to think of restrictions, then I cannot use this kind of language, so I change this. Okay. Now, what about first class? Why did I do all this? I will not use this Dirac brackets, but I will use some other technique which I think is more adapted here, and I will mention that I suspect that it can be used, as I told you, in quantum gravity as well, at least in low dimensions, okay? Because of recent work coming from people like this Raphael's group, and also this Hadamard states and so on. Okay? It seems that low dimension maybe, because you see that it gives a complex structure which we shall see is important for quantizing even particles with spin. So you will be able to divide the constraint into, you will be able to apply maybe a Gupta-Bloiler type procedure. I'll try to show you. Now, why did I do all this? Okay? Back to first class. So the claim is the Poisson bracket of Fi with Fj is Ckij. This could be a function of Q and M, Fk. Okay, I put this could be functions. This is a claim. So I am going to claim. I'll prove it to you. This is claim.
So you're assuming that you have solved explicitly the second class constraint.
Yeah. No. I'll prove this with the second class constraints.
With the Dirac bracket.
Without the Dirac bracket, I'll show it to you. So I didn't put any star in the bracket. Okay. This is true. I want to warn you. All this is very nice and nice. It looks simple, but it is not, because there is no guarantee in a complicated problem that this M. This is not a constant matrix. It depends on the point of the T star M. Could have different ranks at different places. No problem. Okay. If that happens, this whole method will be in trouble, right? I mean, it happens in certain physical contexts. So if you have different ranks, for example, you might have zeros. Its determinant might have zeros. Okay? Then at those points, the rank of M suddenly changes, right? So you have to cut those points out to do this analysis. So the moment you cut those points out in insights, then when you go into quantum theory, you will immediately have manifolds with boundaries, and you will have all this silver joint operators and all kinds of stuff which people definitely loathe. You will have to do all this phenomenon analysis, all kinds of things. Okay? So this happens in some boundaries. Okay? It happens, for example, in gravity. There are no second class constraints. It happens. Similar thing happens with these coefficients. When you do trying to do factor ordering, I mean, you cannot write it like this in quantum theory, because these things don't commute. Okay? So you have to do some ordering. So they may not even close. But if you succeed in closing, these coefficients generally come out as functions on where you are. Then you don't know what happens. Okay? So this is all. This is a very cosmetic way of presenting the material. Okay? Beyond this, you cannot make general statements. Okay? Which is one of the problems of this whole business. But in the cases we consider this, we won't encounter this. Okay. How do I prove this? For suppose okay, Fj, Fi Fj, right? I wrote M and P. The point of the manifold in the phase space. I wrote. Okay. This Poisson bracket had Ckij, okay, Fk, but suppose there were Dk Ij Sk. I will prove that D is 0. Why? Because some question.
No, no. Now this is an identity, right? And it's not weakly 0 in this.
This is an identity. It's not weakly 0 yet. Not weakly 0. Weakly 0, the whole thing is weakly 0.
Yeah.
There is nothing to prove. How do I prove this? Well, use Jacobi. By the way, Dirac bracket is not weak. As far as second class constraints are concerned, the Dirac bracket is a strong equation. Okay. So I am careful in putting tiddles and equalities. Okay. So what is Jacobi? Is something like Fi, Fj, let's say Sk. Okay. Huh?
Only on that part.
Yeah, plus Fj, Sk, Fi, plus Sk, Fi, Fj is Jacobi, so certainly it has to vanish. In fact, it has to strongly vanish. Certainly it has to vanish weakly on the surface. Doesn't matter. This thing here, let's put weakly. It will vanish. Let's put weakly. This thing here, this is a constraint. This is a constraint. Is a Ck, a Cl. This is a Cl. Okay? Because this is a Poisson bracket of a first class constraint with a constraint. So it is a constraint put here. But that has 0 Poisson bracket with the first class constraint. So this whole thing is weakly 0. Same thing goes here. But here you get Sk, then get this Di, this weakly Dij, okay, M times Sm. Right? But this is equal, this is not weakly 0, this is weakly equal to dm ij times this bracket sk with sm, what I called mkm. And this is supposed to be weakly 0. Is m is invertible, okay, dm ij is 0. So the first class constraints look like forming a Lie algebra, closing under commutations. Classically, it will vanish. Okay? That's not the problem. The problem will come when this C is a function of Q and P, as happens in gravity. Okay? The structure constants are not really that of a Lie algebra. Something else is happening. Okay? The Lie algebra is not on complex numbers, if you want to put it that way, but the coefficients are in some functions. Okay. You can define Lie algebra where the scalars are taken from anything. Okay. You can take it from complex numbers, real numbers, what is it? Fields a characteristic P, where P is Suppose you take them from functions, you get this. Then nobody knows what is happening. This is what happens in gravity.
Always we define Lie algebras over a field of integers.
No.
Simply a structure constant.
No. Semi-simple Lie algebras over finite is over. They do all of it. We do it with reals. For example, so real Lie algebras, compact Lie groups over real Lie algebras. Yeah. We do it over complex. Then down the corridor there are people, or second floor there are people who do it on fields of prime character, finite fields. Okay. Periodic I have not seen, but I have certainly seen lot of people doing prime character ZP for P prime. Okay. ZP for P prime is that's a canonical thing that people do. Okay. You can do that. SL2 with coefficients in Z. ZP, SL2 with coefficients in integer, that kind of thing, no? Finite fields they do all the time. Not only we also, in physics also it turns out.
It's textbook.
Yeah, nowadays, nothing to us, right? Yes, but this stuff is a different story. I have not seen anything much here on this. But anyway, so let me understand this here. So, what Dirac suggests? To quantize. Okay. So, we assume there are no second class constraints, or they have been somehow handled, maybe with Dirac brackets, Dirac-Bergman brackets. Okay. So, promote Fj to operators F hat j and constrain vectors in Hilbert space by F hat j acting on the state is 0. Huh? Guttav-Euler. That's what Dirac suggests.
These are just like gates.
Yes. The whole point is this is consistent. Since this F hat j, F hat k is CJKL F hat L. Okay. We cannot do this with second class. Because their Poisson bracket is non-singular. Okay. So you will get a contradiction. Since this equation will give Sj S hat j S hat j S hat k equal to 0 equal to this matrix Mjk equal to 0. So you will get some nonsense equation. Okay. So second class constraints cannot be treated this way, but first class can. Now, if say O is an observable, we want O acting on this Fj is 0 if f hat j, let me call it O hat, f hat j on this state is 0. So we would like, which means O hat with f hat j, okay, is weakly 0, or is a linear combination of constraints, is some psi j k, this could be depending on O times f hat k, by consistency, or O hat commutes with f hat, I mean modulo constraints, okay. So O hat, so this leads to the interpretation that f hat j generate gauge transformation infinitesimal okay, gauge transformations. Yes. Now let me make two remarks on this context. Yeah? First claim is, okay, so classically, so there are two things that happen. The surface sigma, okay, so if let us say sigma some I shouldn't write sigma, if the surface with Fj equal to 0 is, let me call it give me another symbol. Huh? What?
Gamma.
This is gamma, capital gamma, of course. No, none of us, I mean, we wouldn't even imagine putting small gamma. It's gamma. Okay. The canonical transformation, okay, the generated by Fj is tangent to gamma. The vector fields, each Fj generates a vector field, okay, and the vector field is tangent to gamma. Why? Because the f with f is in again f. So gamma is here, this vector field associated to gamma is tangent to the surface. The second class constraints on the contrary will take is transversal to the surface. So this is the major difference between first and second class. So you have got this surface, okay, f is acting, the vector field is generated by f. That's what I mean by the canonical transformations is tangent, the second class is going that way.
Can you please repeat this?
The canonical each fj generates a vector field, that is differential operator with coefficients, okay, and with that we can associate on the manifold vectors, okay, going along the manifold, okay, and they are tangent to the surface because f with f is again in f, whereas the second class ones are transversal because those vector fields don't close on the surface, okay, they are transversal to the surface, okay. But in addition, okay, observables O are constant on orbits generated by f's. Yes, because that's what I said here. Okay. So we are reducing the degrees of freedom by two f's. So if there are k first class constraints, okay, we are reducing, okay, the family of functions, if you want, okay, family of functions by 2k. First f's vanish, but then f's are generating canonical transformations. So there this is the surface where f vanishes, but if I take a point here, f generate canonical transformations, so they move you along this. It's like a sphere. Okay, I take suppose I take a sphere r square minus 1. So f is r square minus 1, this is vanishing. But this might have non-trivial Poisson brackets with a function on this. So it will generate a vector field tangent to the surface. Right? So the function may vanish, but the Poisson bracket it generates is not vanishing, but it is remaining tangent to the surface. Otherwise, I won't have this term. Okay. So it is going tangent. So it is drawing lines on the surface. If you take the vector fields, and the functions I am considering are constant on this. Okay. So first I have reduced the family of functions by setting k of them 0, but then I am requiring that on the orbits the functions are not changing. So the functions I am dealing with are really the quotient of this surface by the orbits generated by f. So it's a bundle structure, right? So what I have done is all of them. Okay. So this is what I call gamma, but I am quotient in this. So this is becomes something else. In fact, I can go. I called it E. Okay. This is a bundle space. What is it? B base space. I called EB. So this goes to B. So this if I call E. Okay. This is my bundle space. The structure group is a group generated by the F's. I am taking quotient and going to B, and the observables are functions on B. If you want complete analysis of the geometrical structure, I should eventually I am only considering functions on B.
So my photons will have two state of products.
Yeah, if you do this. Okay. This way looks beautiful, but unfortunately people who dare to do quantum gravity don't find it very beautiful because it gets a mess. Okay, we will hear a seminar on that from Alok this Wednesday too. Okay, but this is a general schemata. So I have reduced the thing by 2k twice, which is very reasonable because the phase space should be, eventual phase space should be even dimensional. Okay, right? So the at each point the base of functions is still even. Okay, okay, which is by counting. Okay, so this is a general structure. I think I should stop here, but I want next to concretely apply it to particles with spin, okay, and show you how all these things systematically come up. One more thing, then I will stop. That is very important indeed. Okay, physically. In H is H0 plus Vj. You remember the Pj. This must Vj Pj is necessarily first class. This is already known because if you put a second class, then I take the bracket of second class with this, I can determine this. Okay. But I get some equation which can be inverted. Okay. So this will not come. Okay. So this is necessarily first class, and the v's are arbitrary functions. So objects observables with well-defined time evolution necessarily must commute with these constraints, because otherwise you will get arbitrary time dependence. Okay. Observables, okay, functions with well-defined time evolution necessarily, okay, have this equation, okay, functions f. Let me call it O. So O with this Vj Pj, this is classical, must necessarily be 0. A well-defined Cauchy problem can be put only for this O, okay, which means, but this is a condition of gauge invariance. But almost, okay, this is, so this is, that is O, okay, is invariant due to gauge transformations. This is a classical of this object. What you get here?
What happens is this, again forward. If I use secondary constant Sj for example, then what?
They will not appear, or eventual combination here.
Then what happens to this equation? O, comma Vj Sj.
They are, that is why second class constraints therefore are not observable. That
you run through this logic again, that
yeah.
why Vj Pj is necessarily first.
Because if there were a second class term here, suppose I had a term like S, some Sm plus some then I will look at the time evolution of Sl with H. Okay, this will commute with the first class part, but here it will give some Sl with H0, and here it will give this matrix MLM. And I invert it and I'll find these coefficients. Okay, so it may get completely determined. Okay, then it will become something which you know already. Okay, and you can determine the coefficients and yeah.
So it's not really.
No, the time evolution. I mean, eventually, the only thing that can remain here, undetermined with undetermined is necessary. With undetermined Vj, I should say here, with where is with undetermined Vj. I forgot to put this. There may be terms which are second class with determined Vj,
Yeah.
but that
It's
won't.
not a Lagrange multiplier in
Yeah.
sense.
Okay. Undetermined Vj.
But Vj is a Lagrange multiplier you added
Yeah,
in
so
first place.
So it should not be determined by the evolution.
Yeah.
But you have a
But
kinetic part corresponding to this Vj also. You have-
there is no kinetic part.
means this time equation is there. Means it's not constant actually.
No, you can choose anything whatsoever for these Vj's until you look for consistency of constraints and the secondary constraints and so on, and some of the Vj's will get determined. Okay, those things are not, and they will get multiplied by some second class constraints. Okay, some constraints, second class constraints, okay, or whatever. Okay, then some of the Vj's will not be determined. Okay, the ones which are determined, if it is second class, if I go to Dirac brackets, you can set them 0. So all the things where the coefficients are fixed will not play any role, because by the time they are fixed, so I can if they are first class with coefficients, they will get fixed. So you can say it will give only well-defined time evolution. But these objects which have undetermined coefficients will give undetermined time evolution. So you cannot tell past, future from present. They are around. Okay, so this is the deduction that gauge invariance is necessary for putting Cauchy problem, which you were asking today earlier. Okay, now a conjecture of Dirac in his yeshiva lectures is that all first class constraints will appear as Lagrange multipliers in the Hamiltonian. Okay, he could not prove it. That in his analysis, only the primary constraints will appear, okay, here, but H0 also has some other terms, okay, like A0. Some you have to rearrange the whole thing eventually, and you'll find something else. Some secondary constraint will appear and converting some part here into a constraint and all kinds of things. Okay, and there was a conjecture by Dirac that all constraints will appear. Sorry, all first class constraints will appear in the final Hamiltonian with undetermined Lagrange multipliers. Okay. That conjecture is not proved even now, to my knowledge. Okay. And from this point onwards, you can do other things like BRST. I will not do BRST, but you can put some further activities here, which I will not do. But what I will do is concretely show how it applies to spin, and how these things are treated, to magnetic monopause. Then I will shift to problems related to gravity. Okay.
So next Monday I will not be here, so somebody has to take the responsibility.
You will not be here for sure.
For sure.
Okay. Okay.
Next Monday.
Okay.
Next Monday also. Next Monday you will not be here? You will not be here. So can you have to send two emails. It's very tough. You can do it. No. Next one.
Get fix a room also.
Next
Okay.
Monday means next Monday. Coming. No, you just look at the IMSC seminar list and find which room is empty. Yeah. So there's finite number of rooms. So
And send an email also to these people.